All right, so we are continuing to talk about welding and specifically rivets or fasteners. We're talking about rivets, welding, and bonding in this series. And today, in this video, we're going to be going over welding analysis through two examples and how we can calculate weld properties for engineering applications. So one question that might come up in design is, if I have a plate that has a side fillet weld on each side, and I know how long, I know the properties of the weld. Question might be, if I have a fillet weld here on each side of this plate and the same type of weld all the way on the back side of the plate, and I know that this distance here is 50 millimeters. And the question is, what is the max force that can be applied, or what is the force F that can be sustained by the weld? Now obviously we'd have to make sure that for the material properties of the plates that we wouldn't be failing the plates here by fracture at the ultimate strength. But the question is, you know, what force F can the loads sustain if the plates have a yield strength of 350 megapascals and the weld material is a steel recipe that has the same yield strength, 350 megapascals. So the question is, what is the force? And we've learned in the last video that this distance between these, the vertical height of the weld and the horizontal length of the weld, or the toe and the top, that this length here is the throat. That's this distance, T. That's the throat of the weld. And we know that if we have this loading condition with these forces, that this is our shear plane here, and that force is going to be picked up by this area on the sides, and it's going to be in pure shear. So if it's in pure shear, then we really need to change this. This is our yield strength for tension. And if we look at the shear yield and we use the distortion energy theory, then that's about 58% of the yield strength, or about 203 megapascals. We also want to have a factor of safety. So in this case, we'll choose a factor of safety of 3, and we will then just calculate the force, and the force is going to be the max stress times the area over the factor of safety, and the area is the area of the weld, is the shear area. Okay, so, and that is equal to the throat of the weld times the length of the weld, and in this case we have the weld on both sides, so we can either make the length twice 50 or we can just multiply by 2. So in this case the shear area is 424 millimeters squared. And we know that because actually we're given that the leg height is symmetric. Okay, and so this is our leg, H. This is also H, and we're told that H is equal to 6 millimeters. So if we take the leg height and we get our throat area, then our shear area, T, is 0.707 times H times L times 2, which is 100 millimeters, and that gives us our 424 millimeters squared. So if we plug that in and we plug the 203 in to this, and we plug our factor of safety of 3 into here, then we calculate that the max force that can be sustained is about 29 kilonewtons. So I want to make a brief note. You can go and look up and find out how to, if this was a, for example, a stick welded application, you can find out what the stick weld electrode strength is to find the weld material for a problem like this. The American Weld Society, they have the numbering system. So for example, if you were to go to a store that sold welding supplies like Northern Tool or Home Depot or Lowe's, you could find a pretty common stick would be a E6010. The 60 is 60,000 psi, which is about 400, a little over 400 megapascals, and the last 2 digits indicate the type of coating as well as the type of current, whether it's AC or DC, positive or negative, which tells you which direction the current has to go through the system when you're welding and setting up your welder. So this is just some basic information of how we could actually get the tensile strength of the weld from a common material. All right, so that's an example problem. It's pretty simple, straightforward. Shows us how we use the throat area and the weld stick. But question is then, well, what do you do if you have loading, say, like on a plate like this, or some weldment where this weldment is welded to something like a frame, and the weld is here along the vertical and along the top, and so this is our weld here. And if we have a load, say out here. Let's say we have some connection bracket, and on that bracket we have a load, say of 20,000 newtons. The question is, how do we do this analysis? Well, the first thing that you do if you have combined loading, this is called in-plane loading. And the first thing you do is you're going to move this load and put an effective load at the centroid of the weld group. So this weld on the top plus this weld on the side is a weld group, and then there's going to be a centroid of that group, and essentially you move this load, this 20 kilonewton load, over to that location and make an equivalent load and an equivalent torque at that position, and then you can do the analysis on the welds. But what you have to do is move that into the plane. If you have a situation where you have, for example, a out of plane load, let's say we have this scenario where we actually have a similar shaped bracket, but in this case we have that this bracket is out here, and we have a weld that goes all the way around. So let's say we have a weld that goes all the way around, and let's say it goes over the whole thing, and then this is welded to some backplate, and let's say we have a load here in the middle of something like, say, 10 kilonewtons. The question is, well, how do we analyze this load? So when the load doesn't pass through, when it's an eccentric load, and you take the center of your weld group and you move the load to the center and you replace it with the load plus the in this case this is the out of the plane. So if this is the X and this is the Y, then this bending moment is in the Z plane. You replace it with that load and then that bending stress that's applied. And then you look at the bending stress here that would be applied from this position relative to that center of the weld group, and then do the analysis that way. So these are assumptions about how we analyze this, and this is sufficient for most engineering design work. In order to do the analysis, we have to be able to calculate the shear stress due to the torque applied to that load group in the in-plane case. So this relates to the in-plane case where we want to find the shear stress, and that's the torque times the distance to where it's applied from the centroid over J. And this is the moment of inertia. In this case, this is the polar moment of inertia. And we have to find the bending stress sigma due to the bending moment over here. And that's just the bending moment times the distance from the neutral over I, and that's the moment of inertia. And that's the moment of inertia of the weld group. And we're going to have to explain this a little bit better. But the activity involves finding this location, okay, at the center of the weld group, and that's the centroid X hat, Y hat of that group. So, in case you've forgotten how to do that, we can take a look at that. So we'll do that through an example. So let's say we have that same geometry that we had just showed, and we have a bracket, and this bracket has a weld here at the top and a weld on this back side, and that it's welded to a plate, and the plate, let's erase that there, the plate is behind here, and we have a load that acts somewhere out here, and this load is the same as it was, it's 20 kilonewtons. And we want to look at how thick the weld should be. So how thick of a weld do we need if we use a E60 stick for stick welding. So the first thing we need to do is find the centroid of the weld group X hat, Y hat, because what we're going to do is move this force over to that. So it'll be 20 kilonewtons, and it'll have an applied torque. So we're just making an equivalent loading condition that's out here in the end, but we're doing it with respect to this centroid so that we can calculate the moments of inertia and polar moments of inertia relative to that centroid. So to find the centroid X hat position, we can just use the discretized formula for finding the centroid for each area. It's the sum of the areas times the distance x to that area over the sum of areas, sum of all the areas. Okay, so in this case we're told that this distance here is 150 millimeters, and this distance for the top weld is 100 millimeters. Okay, so we have a 100 millimeter top weld and we have a 150 millimeter bottom weld. We're trying to find the centroid X hat, Y hat. So we use the formula for the centroid here, and we look at the X weld. In this case, the X weld is 100 millimeters, and the weld area is what we use, and the weld area is the length of the weld times the throat of the weld. And so that's the question: how thick of a weld do we need? And we know that if we have a symmetric weld, that the throat of the weld is 0.707 times the leg of the weld, and the leg of the weld is how thick the weld is, or the height of the weld. So that's your H, and then this distance here is your thickness, right? So we're trying to find that information, so we'll just leave that as a variable. So we have 100 times the throat, that's the weld area, times the distance if we pick this as the origin up here at the top left corner. So if we say that we're calculating the centroid with respect to a y here and an x here, so this is y0, the top left corner is y0 and x0, then we're going to calculate the centroid with respect to this position in x and y in this plane. So we can just do that by calculating that distance. So the distance in x to that weld group here is just going to be half of that, which is times 50. And then we need to calculate the other weld, and so in that case we're going to add this weld group, which is the vertical weld group, and that's going to be 150 times T, and half the weld is going to be on the positive side of that axis, half of the weld is going to be on the negative side, so it's going to be some small delta, that's half the weld width, minus the delta, which is that weld width, which means that this entire term just goes to 0 because this distance works out to be 0. And then we divide that by the sum of areas, which is just the 100t plus 150t. And that gives us our x centroid, and the x centroid works out to be 20 millimeters. We do the same thing with y. We want to find the y centroid. It's just the sum of the individual areas times the distance in y to those areas over the overall area. And in this case we look at the top weld group, and for the same reason we have the 100 times T. Then we have that plus minus delta because half the weld is above, half the weld is below, so it's 0. That's the effective distance from y of that weld group. So we're looking at this weld group is along the y equals 0 axis. And then we add the vertical weld group, which is 150 times T, and then that's times the distance to that center of that weld group, which is going to be here, which is half of 150, which is 75, over the overall area, which is the same, which is 250t, which gets us the centroid of 45 millimeters. So what that tells us is that the centroid is over here, that this is 20 in x, so this position is 20 and 45, and that's with respect to the top left corner. Okay, so then using that information we can calculate our moments of inertia, and before we do that we can review the parallel axis theorem. And so for example, if we have a object like this, which looks kind of like a weld group, and it is at a position that is over from where we want to calculate this position. Let's say if this is our x hat and this is our y hat and this is our x prime and this is our y prime axes, then we can use the parallel axis theorem to look at if the centroid was here, we calculate it and we just move it over. So you probably might remember you can do your IY bar is equal to your IY prime plus A times your distance squared. And in this case, we're going to call this distance A, and we'll call this Y distance B. So this is for IY, and for IY we have to look at the distance from that Y coordinate. If we wanted to find IX bar, we would find IX prime, IX prime plus A B squared. So that's how we would use the parallel axis theorem. If we were to calculate this here, we wanted to find our Ix hat, then we would just use that parallel the centroid calculation, the moment of inertia calculation, which is just the distance from that y squared dA, and if we integrate that over the half the distance and double it from 0 to L over 2, that's just y squared times t dy, and that equals L cubed t over 12, which is the same thing that we get for a rod, which is BH cubed over 12 for a similar cross section. In this case, the IY hat is just 0 because the x distance is 0 for that case, because it's sitting here on the axis. If we wanted to look at the polar moment of inertia, we'll recall that the polar moment of inertia is the sum of the Ix plus Iy inertias. So we can use that to calculate our shear and bending stresses. In this case, we have in-plane stress, so it's just replaced by an in-plane downward force, which will cause a shear, and then a torsional torque, or a torque that causes shear stress. Okay, so then with that review in mind, we can take a look at the top weld. And the top weld, if we wanted to calculate RJ, we need the sum of our Ix hat plus Iy hat, which is equal to the sum of Ix plus a dx squared, where dx is the distance to the x squared, plus the sum of the Iy plus a distance to y squared. So we'll look at the welds individually. So for the top weld, with respect to the centroid, we can calculate this as the 100 cubed times t over 12 plus 100 t, which is the area, and we'll take the distance to x, which is going to be the middle of that weld group minus where the centroid is, which is 20, and that's squared. We're going to also add the distance to the Y, which is just 45 millimeters down from where that is, squared. And this is equal to 375,833 times T. Then if we look at the polar moment of inertia for the side, this is equal to 150 cubed times T over 12 plus the area plus the distance from the side weld to the centroid, which is 20 squared, that's the delta x, plus the delta y, which is 75 minus 20 squared, and that works out to be 250 T. So J is the J from the top plus the J from the side, which is equal to 852,083 times T. And when we evaluate that torque on the bracket at this location for the X and Y bar, we have 20 kilonewtons, and we have a torque, and this torque is this load was applied at a distance of 280 millimeters, which makes this torque 20 kilonewtons times 280 millimeters, which is 5,600 Newton meters. So we need to also consider the direct shear. So we have to consider the combined load for direct shear, and the direct shear is just the shear stress, tau, which is V over A, and that direct shear is going to be 20 kilonewtons over the area, which is 100 times T, plus the 150 times T, which is over 250 T, and that gives us 80 over T. So that's the direct shear, and that acts on all of the weld. So that shear is acting on all of the weld here. And sorry, that's not drawn to scale. This is 150 and this is 100. Okay. And we also need to calculate the shear due to the applied torque distance to the applied torque times the J that we just calculated for the polar moment of inertia for that weld group. So what we do is we take a look at the weld group, and we have the top weld, and we have the side weld, and we have this load here at 20 kilonewtons and this torque at 5,600 Newton meters. We just talked about how do we find this location for X bar and Y bar, and we just talked about how do we find J using the parallel axis theorem, considering this is the origin, and finding these distances to the centroid, and then moving these top and side weld polar moment of inertias, those distances. So that's what we just did. So now to get the stress at each location, we can look at the shear at those locations. And if we do that, we find that we have at this point, we'll call this point A. We'll change the color here. We'll call this A, point A. And we'll call this point B. And those are the maximum distances from this centroid where that torque is applied, and that's going to be where the maximum shear stress is present. And so we're going to take a look at those points. Okay, so if we look at point A, and I'm just going to redraw this over here, that this is our weld group. This is point A. This is point B. Here's the centroid with the downward load in the weld group. And we can calculate the loads. So the loads here are going to be the constant shear for both of those, for both A and B. That's our shear due to the V over A, which is 80 over T, which we just calculated. So that's the yellow portion. And then we're going to have another portion that's due to that applied torque or torsional load on that joint. So this distance here is 45. This distance here is 20 from our calculations to get there. So basically we have a torque here that is T R over J, and in this case the distance R is 45. So we write 45 over J. And then we have this torque here, which is going to be the 100 minus 20, which is T times 80 over J. And we're going to have a resultant of those two torques. We're going to have to also include this torque. We'll do that in a second. But this resultant here is T times square root of 80 squared plus 45 squared over J. And if we look down here, we have this shear, and then we have an upward stress that's T times 20 over J, and then we have a stress in this direction, which is T times 105 over J, and then we have another resultant of those two. We also have to include this shear value, but we'll do that in a second. And this is T times the square root of 105 squared plus 20 squared over J. If we resolve these, we find that actually point B has larger value of stress, and if we resolve the stresses at point B and we include the torsional stress, what we get is this bottom portion, which is 690 over T. We have a small upward value, which is the 131.4 over T minus 80 over T. And then we have this resultant, which was the one that we care about, which is 691.9 T. And then, so we can say that the state of stress at B is equal to 691.9 T. If we select a safety factor equal to, say, 2.5, then this allows us to calculate the thickness of the weld joint, because we are told that we have an E60 weld rod, and that gives us a 60,000 PSI strength. And that is the tensile strength, which is actually the ultimate tensile strength. So we have to take the yield stress to define failure. So I think tensile strength is a little bit over 400 megapascals. So if we look at the yield stress, then we have to say that, oh sorry, this is 691 over T. 691.9 over T. So we have to say that the state of stress at B is 691.9 over T, and it has to be equal to the yield stress, which is going to be, if it fails in shear, we take the yield stress, which is about 345 megapascals. Using the distortion energy theory, we calculate 58% of that, and then we divide it by the safety factor. In this case it's 2.5, and then we can solve for T. So this tells us that we have to have a throat of about 8.65 millimeters, and that's equal to 0.707 times H. So then that tells us what the leg of the weld has to be, and that H has to be 12.23 millimeters. But welds are specified in whole numbers usually, so that would be 13 millimeter weld in order to meet those requirements.